In a single-phase circuit operating at 208 volts, when calculating voltage drop, it's crucial to understand how the wire length affects the calculation. The fundamental principle is that the current travels from the source to the load and then returns to the source, completing the circuit. Therefore, the total length of the conductor involved in the voltage drop is the sum of the outgoing and return paths. In scenarios like this, where the load is 20 amps and the linear distance from the source to the load is 600 feet, the total conductor length for voltage drop calculation becomes twice the linear distance. This is because the current must travel 600 feet to reach the load and then another 600 feet to return to the source. Consequently, the total conductor length to be considered for voltage drop calculations is 1200 feet. The formula used to calculate voltage drop in a single-phase circuit is voltage drop equals 2 times the current times the resistance per unit length times the length of the conductor. The factor of 2 in the formula accounts for the outgoing and return paths of the current. The resistance per unit length is determined by the wire gauge, material, and operating temperature. The length is the total conductor length, which is twice the one-way distance in this case. To accurately assess voltage drop, you need to know firstly the load current in amps, secondly the total conductor length in feet, and thirdly the resistance of the conductor per foot. The conductor resistance is dependent on the wire gauge, material, and operating temperature. For example, let's consider a scenario where you are using number 12 American wire gauge copper wire. You would need to consult a wire table to find the resistance of number 12 American wire gauge copper wire per foot at the operating temperature. Once you have this value, you can plug it into the voltage drop formula. In cases where the voltage drop exceeds the acceptable limit, you may need to increase the wire gauge to reduce the resistance per foot. This will decrease the overall voltage drop in the circuit. Alternatively, you can reduce the length of the circuit, if possible, to minimize the voltage drop. However, in many practical situations, the circuit length is fixed, and the primary means of controlling voltage drop is by selecting the appropriate wire gauge. It is also important to consider the National Electrical Code, or NEC, guidelines for voltage drop. The NEC recommends that the voltage drop on feeder conductors should not exceed 3%, and the voltage drop on branch circuit conductors should not exceed 5%. These recommendations are intended to ensure that electrical equipment operates correctly and to prevent overheating of conductors. When performing voltage drop calculations, it's essential to use consistent units. If the current is in amps, the length is in feet, and the resistance is in ohms per foot, then the voltage drop will be in volts. It is also important to account for any splices or connections in the circuit, as these can add to the overall resistance and increase the voltage drop. Splices and connections should be made properly and be of high quality to minimize their resistance. In summary, for a single-phase 208-volt circuit, the length of wire used to calculate voltage drop is twice the linear distance from the source to the load. This is because the current travels out to the load and back to the source. By understanding this principle and using the correct voltage drop formula, you can accurately assess voltage drop and ensure that your electrical circuits operate safely and efficiently. Furthermore, remember that factors such as wire gauge, material, operating temperature, and splices or connections can all affect voltage drop, so it's important to consider these factors in your calculations. Let's delve into some additional aspects of voltage drop calculations and how they relate to practical applications. Firstly, consider the impact of different conductor materials. Copper and aluminum are the most common conductor materials used in electrical wiring. Copper has a lower resistance than aluminum, which means that for the same wire gauge, copper conductors will have a lower voltage drop compared to aluminum conductors. However, aluminum conductors are lighter and less expensive than copper conductors, so they are often used in applications where weight and costs are important considerations. When using aluminum conductors, it's important to select the appropriate wire gauge to compensate for the higher resistance and ensure that the voltage drop remains within acceptable limits. Secondly, consider the effect of temperature on conductor resistance. The resistance of a conductor increases with temperature. This is because as the temperature increases, the atoms in the conductor vibrate more vigorously, which impedes the flow of electrons and increases the resistance. The temperature coefficient of resistance is a measure of how much the resistance of a material changes per degree Celsius or Fahrenheit. Copper has a lower temperature coefficient of resistance than aluminum, which means that the resistance of copper changes less with temperature compared to aluminum. When performing voltage drop calculations, it's important to account for the operating temperature of the conductor. This can be done by using the appropriate temperature correction factor in the voltage drop formula. Thirdly, let's examine the impact of different types of loads on voltage drop. Resistive loads, such as heaters and incandescent lights, draw a constant current, which makes voltage drop calculations relatively straightforward. However, inductive loads, such as motors and transformers, draw a current that varies with time, which makes voltage drop calculations more complex. Inductive loads also cause a phase shift between the voltage and current, which can further complicate voltage drop calculations. To accurately assess voltage drop for inductive loads, it's important to consider the power factor of the load. The power factor is a measure of how effectively the load uses electrical power. A power factor of 1 indicates that the load is purely resistive, while a power factor of less than 1 indicates that the load is inductive. The voltage drop for an inductive load is higher than the voltage drop for a resistive load with the same current and conductor length. Fourthly, let's discuss the use of voltage drop tables and calculators. Voltage drop tables provide pre-calculated voltage drop values for different wire gauges, conductor materials, currents, and lengths. These tables can be a convenient way to quickly estimate voltage drop without having to perform detailed calculations. However, it's important to note that voltage drop tables are based on certain assumptions, such as a specific operating temperature and power factor. If the actual conditions differ from these assumptions, the voltage drop values may not be accurate. Voltage drop calculators are software tools that allow you to input the circuit parameters and calculate the voltage drop automatically. These calculators can be more accurate than voltage drop tables, as they can account for a wider range of factors. However, it's important to ensure that the calculator is using the correct formulas and assumptions. Fifthly, let's talk about practical examples of voltage drop calculations. Consider a 208-volt single-phase circuit supplying a 10 horsepower motor located 100 feet from the source. The motor has a full load current of 28 amps and a power factor of 0.8. To calculate the voltage drop, you would need to determine the appropriate wire gauge based on the NEC ampacity requirements. Let's assume that number 8 American wire gauge copper wire is selected. You would then need to find the resistance of number 8 American wire gauge copper wire per foot at the operating temperature. Using the voltage drop formula, you can calculate the voltage drop and determine whether it exceeds the acceptable limit. If the voltage drop is too high, you may need to increase the wire gauge or reduce the length of the circuit. Sixthly, consider another example involving a lighting circuit. Suppose you have a 208-volt single-phase circuit supplying a series of LED lights located 200 feet from the source. The total load current is 15 amps. To calculate the voltage drop, you would need to select the appropriate wire gauge based on the NEC ampacity requirements. Let's assume that number 12 American wire gauge copper wire is selected. You would then need to find the resistance of number 12 American wire gauge copper wire per foot at the operating temperature. Using the voltage drop formula, you can calculate the voltage drop and determine whether it exceeds the acceptable limit. If the voltage drop is too high, you may need to increase the wire gauge or reduce the number of lights in the circuit. Seventhly, let's briefly discuss the use of step-up and step-down transformers in relation to voltage drop. Step-up transformers increase the voltage and decrease the current, while step-down transformers decrease the voltage and increase the current. By using a step-up transformer at the source and a step-down transformer at the load, you can reduce the current in the circuit and minimize voltage drop. This technique is often used in long-distance power transmission to reduce losses and improve efficiency. In conclusion, understanding voltage drop calculations is essential for designing and maintaining safe and efficient electrical circuits. By considering factors such as conductor material, temperature, load type, and circuit length, you can accurately assess voltage drop and ensure that electrical equipment operates correctly. The National Electrical Code, or NEC, provides guidelines for voltage drop, and it's important to adhere to these guidelines to ensure safety and prevent overheating of conductors. Remember to double the one-way distance to account for the current traveling to and from the load.